So I know you must all be thinking, wow, how cool. We get this uninhibited flow of electrons flying through a wire to light our entire city, to light our entire world. How cool is that? Well, not so fast, because there's something that's always working against conductivity, and that thing is resistivity. Every material has a certain amount of resistance, with one caveat. There's one kind of material that has no resistance. It's called a superconductor, and in order for it to work, you need to get that material down to, many tens of degrees below zero. And at present time, unless we all want to live in a giant refrigerator, we have to deal with our materials having some resistance. And so why? Why is there resistance? Well, there's a couple reasons for it. One is that not all materials are created equally, right? You have some materials where the electrons are more bound to their valence shells, and some materials where they're less bound, therefore it takes less energy for them to flow through, right? You also have, not all materials are perfect. You have some impurities in certain materials, and so as the electrons are trying to get through, they're like knocking into things, running into things, right? And so it's almost like a lineman in football, American or European football. I guess it's not European football, it's world football. It's called a World Cup. Why do we say European football? I don't know. Anyways, so here's the thing. We have these certain materials, most materials, that have a certain amount of resistive effects, okay? And that resistivity depends on a lot of things. One of the things that it depends on is the temperature of the conductor. So if you would go to the slide that says resistivity depends on the temperature of the conductor, I want to share with you that there is a relationship between the resistivity, and by the way, resistivity is usually measured with rho. At this point in physics, you're like, I've seen that before. That's density, Stambach. Density. Do not confuse me. Well, I apologize. Physics is like that. When you get to a whole other field of physics, a lot of times they start reusing the variables because there's only so many letters and Greek letters out there. So unfortunately, in this case, rho is resistivity. Okay. Now, resistivity of a certain material is equal to its base resistivity, right? Its reference point at temperature T0, which is basically room temperature, right? Times 1 plus alpha. Alpha is the temperature coefficient of resistivity. So this is something that is a property of the material. This alpha here depends on the material itself. And so you'll have tables where every material, every conductor out there will have a certain alpha associated with that. So it'll be either something you can look up or it will be given in a different problem, right? So it's alpha times the temperature that you're at minus the reference temperature. Okay? So in other words, this term right here is going to change the resistivity at the reference temperature by this factor, okay? And so how does this work exactly? How would you see this change in resistivity happen in real life? Well, of course, I have a problem for that. And if you go to the slide that says tungsten, we'll just use tungsten as an example. Tungsten is a conducting metal that bros often resort to for wedding band purposes. It's a very common male wedding band material. It has a temperature resistance coefficient of 0.0045. So in other words, in this case, this is 0.0045. Okay. So let's say that the bro goes from San Diego, which is room temperature, all right, that's our reference temperature, to Hawaii, where the temperature is higher, and he just happens to measure the resistivity of the ring, as he does. And he finds that after measuring the resistivity at this place, he finds that it is actually 6.05 times 10 to the minus 8. All right. What is the temperature in Hawaii? So that means, in other words, we're trying to figure out what this is right here. All right. So what do we do here? What do we do? Well, we just want to solve for T basically, right? First thing you want to look at though is what is the reference temperature? T0 is just going to be 20 degrees Celsius, right? For these problems, you can use Celsius or Kelvin, but you know, in chemistry we typically use Celsius. Let's go with Celsius. All right. So we know the reference temperature. In other words, we want to be able to solve for the temperature in Hawaii. This is in Hawaii. If we're finding that the resistivity of tungsten is this. Now, there's one more thing we need to be able to know in order to solve this problem, and that is what is the resistivity of tungsten at room temperature? All right, this is something also that you would just look up in a table. I have done that for you already, and I found out that the resistivity of tungsten at room temperature is simply 5.25 times 10 to the minus 8 ohm meters. And a couple things here. By the way, this is ohm meter is the units for resistivity. Ohm is the unit for resistance in general. And we're going to talk about the difference between resistance and resistivity in the next video. But for now, just know that the units of resistivity is ohm times a meter. Okay? And so now all we have to do is plug this into here. Okay? This is this. T0 is 20 degrees Celsius. Alpha is 0.005. I'm filling up a lot of the screen here, so I am just going to go ahead and say that once I solve this, right, I divide by rho 0, subtract 1, divide by alpha, add T0, then I get a temperature in Hawaii of 53 degrees Celsius. That's pretty warm. That's pretty warm. That would be an unusually hot day in Hawaii, but you know, I wanted to make a significant difference for the sake of this problem. And so we see here that this fellow who had this tungsten ring, just by the mere fact of going to Hawaii, that tungsten has a different resistivity. And in the next video, we're going to find out that if it has a different resistivity, it's going to have a different resistance, which means that if you connected it to a circuit, a different current would flow through it. But for now, in this video, all I want you to know and understand is that resistivity is a property of every material. All right, each material has its own resistivity, and that resistivity happens because electrons are either more tightly bound or less tightly bound to their valence shells, and because there's certain impurities that make it harder for the electrons to move through the conductor, and that resistivity is dependent upon temperature. Okay, those are the three things I want you to take away from this video. In the next video, we'll talk about resistance. See you there.